This lesson is about right triangle trigonometry. So first of all, if you have a right triangle and you have an angle that's one of the acute angles, then of course this side's called the hypotenuse, the one opposite the right angle, and the side opposite of the angle theta is the opposite, and then the other side that's next to the theta is called the adjacent. And of course sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, tangent theta is opposite over adjacent, and you remember it with this funny word, SOHCAHTOA. So if you memorize that, you can get all of this. So now let's solve for x in these diagrams. So if you look at this first diagram over here, the angle 32 is the one we know. This side is the hypotenuse, this side is the adjacent. So really I'm going to use cosine of 32 equals adjacent over hypotenuse, which in this case is going to be x over 7. And of course I can multiply both sides by 7. So 7 cosine of 32 degrees is going to equal x. And I make sure the mode of my calculator is in degrees, and I plug this into the calculator. And rounding to 3 sig figs, I get x is approximately 5.94 centimeters. All right, in this next example, I noticed that from the 64, this is the opposite, this is the adjacent, so I'm going to use tangent. So tangent of 64 degrees equals opposite over adjacent. In this case, opposite was 5, adjacent was x. So let's just call tangent 64 over 1, and now I cross multiply, so x times tangent 64 equals 5 times 1, which is 5, and I divide both sides by tangent 64, so x equals 5 over tangent 64 degrees. And again, if the mode of your calculator is still in degrees, you're all set. Plug this in the calculator and round. And I get approximately 2.44 centimeters. All right, so now we're trying to find the angle, theta. So in this diagram, from theta here, this is the opposite, this is the hypotenuse. So I'm going to say sine of theta equals opposite over hypotenuse, which of course is going to, in this case, be 2 over 3. And to calculate theta, we do sine inverse on the calculator. So we hit the second button and then the sine inverse button, which is right above the sine. And then we plug in the 2/3. So we're doing sine inverse of 2/3. And then we're plugging that into the calculator and getting our answer. When rounded to 3 sig figs, it's approximately 41.8 degrees. Now in this example, from theta, this is the opposite, this is the adjacent, so I need to do tangent of theta. So tangent theta equals opposite over adjacent, so it's going to be 10 over 7. And again, to calculate theta, I do tangent inverse of 10 over 7. And again, I plug that into my calculator. It's once again going to be second, and then there's the tangent inverse button. And after rounding to 3 sig figs, I get approximately 55.0 degrees. So now you won't always have a right triangle to work with, but there are things that you learned in geometry that allow you to put right angles into diagrams. And I'm not going to be able to cover all the scenarios, but I'm going to try to cover a decent chunk to remind you of what could happen, where you can put a right angle into a diagram and then use your SOHCAHTOA, because now you've got a right triangle. So for example, if I've got this isosceles triangle, if I draw an altitude from the top, from the vertex there, between the two isosceles sides, or two congruent sides, and I make this go down to the middle like that, then this becomes a right angle. So I can create a right angle by cutting it right down the middle, bisecting the side on the base in this scenario. Now this would also work for an equilateral triangle, because an equilateral is just a special kind of isosceles. Now this is a rhombus, and you might remember for a rhombus, when you draw the two diagonals of the rhombus, they are perpendicular to each other, so there's how you can get a right angle out of that. The same kind of thing will work with a kite. If you draw the diagonals of a kite, you will also get a perpendicular or right angle. Now here what I've got is a line segment that is tangent to the circle right there. That's key, tangent to the circle. And of course, this dot here is the center of the circle, so that makes this a radius. So the radius and the line tangent to the circle at that point, those are perpendicular to each other, so there's a right angle right there. Now in this circle diagram, what I have is I have a diameter, it goes through the center, and then I have two chords that have a common vertex over here, and it turns out that that angle there is a right angle, and there's some geometry reasons for that, but I'm not going to get into that right now, but that is a right angle right there. Now here I've got a circle with a center here and a single chord, and it turns out that I can actually create an isosceles triangle here like this. Those are the two radii, so those two are congruent. And because of that, I can now do the exact same thing I did up here, which is I can bisect the chord like that and make a right angle over there. Now this one over here is supposed to be a rectangle, so you'd have to be given that information. A square would also do, and of course we know there's a bunch of right angles in a rectangle, so there's a bunch of these like this. And to make a right triangle, for example, you could draw one of the diagonals, and then you've got a right triangle over here. That's how you can, there's some examples of how you can create right triangles and then use trigonometry in your problems. So here are some examples. So here I've got an isosceles triangle, and I'm looking for the angle which is called alpha. So to find that angle, I need to cut this isosceles triangle in half this way by going through the midpoint of that other side of the base, and that makes a right angle. So now what I'm going to do then is I'm going to redraw just one of those right triangles. Let's draw the one that's at the bottom. So it looks like this, and then the thing I drew, which is like that. There's the right angle. And now this is going to be 8.3, and now this side is going to be half of the 5.2, so it's going to be 2.6. And this angle now, well, the whole angle was alpha. I just cut it in half, so that angle there is alpha over 2. Now in this triangle, I know that alpha over 2, that's the opposite, that's the hypotenuse, so I can say sine of alpha over 2 equals opposite of hypotenuse, so 2.6 over 8.3, and now I can do sine inverse to get the answer. So alpha over 2 equals sine inverse of 2.6 over 8.3, and I'm going to plug that into my calculator and keep all the decimal places. So alpha over 2 equals 19.71546709. Now I multiply both sides by 2 to get alpha, and now I'm allowed to round because it's the final answer, 39.4, and alpha was an angle measure, so degrees. So once again, I made that perpendicular and bisector here, the perpendicular bisector basically, and also cut the angle in half, and then I drew just one right triangle from that, and then used my trig to work out pieces, and then went back and figured out what I was missing. Now this here is a trapezoid because of the parallel sides, and there aren't any obvious right angles in a trapezoid, but you can always make an altitude from a point to any line. So I can make that altitude, and I can make that altitude, and what that accomplishes is it gives me a right triangle on this side and a right triangle on this side. And then if you think about it, you got these two parallel sides, and because of those two perpendiculars, you also have these two parallel sides. In fact, you have a rectangle over here. So whatever length this is, that's also the same thing. So if, let's say I call it A, this is also A. So what I'm going to do is I'm going to use this triangle on the left to calculate A using trigonometry, and then use that answer to then do trigonometry again on the triangle on the right to work out what X is. So let me redraw the triangle on the left. Triangle on the left looks something like this, where I have 65 degrees here, I have my 10 centimeters here, and I'm looking for the A. And so I can use, in this case, opposite over hypotenuse. So sine of 65 equals A over 10. Therefore, when I multiply both sides by 10, I get 10 sine of 65 is equal to A. And I'm going to go ahead and plug this in the calculator and keep all the decimals that the calculator reports, which is 9.06307787. Now, I'm going to use that now over here. So I'm going to redraw that right triangle. That's going to look something like this. And of course, this was the same A as before. And this is now 48 degrees. And I'm looking for X. So in this diagram, 48 degrees, I have opposite over hypotenuse. So once again, I have sine, but this time sine of 48 is going to equal A over X. Let's call that sine 48 over 1, and we can cross multiply. So X times sine 48 equals A, and divide both sides by sine 48. So X equals A divided by sine 48. But of course, A is this number 9.06 whatever. So really, X equals 9.06307787 over sine 48. And I can plug that into my calculator and now round it to the required 3 sig figs. X is approximately 12.2, and the units here are once again centimeters. Right, in this diagram, I notice that I've got a circle with a radius and another radius. I'm looking for this distance. Well, if these are both radii, that makes this an isosceles triangle. Therefore, what I can do is I can do the perpendicular bisector right there, which splits this in half. But it also, what it does is it cuts this angle in half. So now let me redraw one of those right triangles. I'm going to draw it a little bit big to be able to fit things in. So I'm going to draw this one. There's my right angle. Now this angle over here is half of that 112 degree angle, so it's 56 degrees. And of course, this is still 6.5. And then this distance over here is half of the A, so it's A over 2. And now in this triangle, I notice from the 56, that's the opposite, that's the hypotenuse, so I can use sine of 56. So sine of 56 equals, opposite is A over 2, and then over hypotenuse, which is 6.5. And now I'm going to multiply both sides by 6.5. So 6.5 sine of 56 equals A over 2. And then I'm going to multiply by 2. So 13 sine of 56 equals A. And again, I plug that into my calculator. And when I round that to 3 sig figs, I get A is approximately 10.8. And the units here were meters. So once again, you start to see how you put your right angles in the diagrams and then you create a right triangle that you can solve. And you then have to sort of relabel things a little bit based on any changes that might have occurred. And that's the end of the lesson.